Okay, so I guess my presentation, the goal is to get the green figure, the charge carrier dynamics. So to get the green figure, there are 7 steps. I guess step 1 and 2 is just pretty straightforward. You just download the necessary input files. In step 3, we just decompress the coupling files and plug them into the MATLAB code, and just run code as Amir and other people have already discussed. So after running this code, we'll have RRR file, which will be input for the actual dynamics. So I guess one major difference between spin polarized and spin restricted calculations is we have 2 components. We have spin up and then we'll have spin down. So basically you need to practice this code twice, one for alpha and one for beta component. So I guess another difference is when we do the actual dynamics calculations, we need a band-out file. And also for spin polarized calculations, we need to separate the alpha component and the beta component. So to create the band-out file, we just run wasp to get the partial charge files. And then after we have the partial charge files, we can run this script. So I guess you need to modify the script a little bit. You need to specify the range of orbitals. I guess it is in line number 14. So after we run the code, we'll have 2 files, band-out diff and a band-out sum. And both these files are needed for the dynamics calculations. So here I show all the necessary files for the dynamics calculations. You need the RRR, band-out diff, energy part, band-out sum, and also a special MATLAB code file. So I guess in the MATLAB code, you just need to modify Fermi energy and also some parameters like the grid points. And this is standard practice, so you need to modify HOMO, LUMO, and orbital interests. So the next step is just to identify transitions and modify these lines. So typically we use bright transitions, which means when you do the calculation of absorption spectrum, you have the oscillator strength file, right? So basically you just choose the transitions with high oscillator strength and use them as input for dynamics calculations. So here is initial hole equal to 1 and initial electron equal to 8. So here is our actual results. So basically after you run the code, the rates for electrons and hole will pop up. So in this case, we have 3 figures. So this one is just the energy level diagram. The middle is the dynamics for in energy for hard carriers. And the third one is the dynamics for hard carriers in space. So any questions?
Okay, please join me in thanking Yulun. There could be lots of questions because it is subject of the future.
So I have two questions. So first, how could we repeat this calculation for systems that are not spin polarized? So
I guess the code is modified a little bit, but I guess so instead of band out diff and bottle sum, you should have only one band out file. And in fact, this band out is not necessary if you are only interested in the dynamics in energy. So this band out file is only necessary if you want to check the dynamics in space.
So that per file, that PL file is available for no spin systems in the bin directory also?
I guess there is a different version in the bin directories for spin restricted.
Okay, thank you. And may I have another question, Dr.
ahead.
Han? How do you interpret the latest figure that you calculate? What we can learn from this figure? Why it's important?
So basically, at the initial time, this is your location of your population. So for example, this is the energy for your initial state. Like here, this is HOMO, and this one is LUMO plus 7. Because this is consistent with your settings. And as time goes by, because energy is dissipated due to lattice vibration, the energy will just go down, right? This is your energy for initial hot electrons. As time goes by, it will just approach from LUMO plus 7 to LUMO. So what's the meaning of this red values? This is just way fitting this curve using single exponential function. So this basically tells you the lifetime of hot electrons and hot holes. The reason this is not available because in this case, the initial hole just sit at a HOMO. So there is no other place this hole can go. So it just stay in the HOMO forever.
And what's the right panel? Z here?
It's just project the occupation of the location of hot electrons and hot holes in your system in the Z directions.
So Amir, for your project of PDPP to PCBM electron transfer, the analog of the right figure will be the main output. Image that Yulun, may I explain the figure?
Yeah, go ahead.
Okay, thank you. So the color code is the same, and I bet this is for one of the organometallic complexes.
Yes.
Okay, so the color code in the right figure is the same as in the center. So red means electron, blue means hole. And the electron is located in the space between 0 and 1 angstrom along the direction, and the hole is located nearby, below 0 and above 1. And as time goes by, this distribution doesn't change substantially. The spatial location of electron and hole remain approximately the same, because this is a neutral system that doesn't
any charge transfer?
No charge transfer. But in the models which are designed for charge transfer, like yours, combination of buckyball and conjugated polymer.
Acceptor unit, yeah.
Yep, these stripes will start diverging into different areas of space. And the length, how far they diverge, and time when they diverge will be most important output of your calculations.
Okay, I got your point.
It looks like Amir has more questions.
Yeah, and both of these figures are output of the MATLAB code that you showed, Dr. Han, right?
Yes.
That MATLAB code could be used for the no spin calculations?
With some modifications, but I guess there is a special version in the bin folder.
Okay, thank you. Thank you for presentation.
And Yulun, may I ask you to go one slide back? Yes, and here is another note for Amir. So at the bottom, you see this IH equals 1, IE equals 8. Right?
Mm-hmm.
So in practical sense, when every input data are already set up, all parameters are set up, the only thing that you modify are these two numbers, IH and IE. And depending on these parameters, it models excitation of your system at different wavelengths. And the rates and distance of charge transfer will be depending on these parameters. So in a very narrow sense, the generation of scientific data for research will mean to rerun the code with different settings of this IH and IE parameters. So this greenish figures on the next slide needs to be recomputed again and again with different values of this IH and IE parameters.
Thank you.
More questions to the speaker?
One quick question.
Please.
So how long should we run the simulation to have that greenish plot? So those one, for instance, 1,000 time step is enough to get that result?
How long? It's basically the same as you computed the triple R.
So it will be quicker than correlation function. It will be almost instantaneous on any laptop. More questions? 1. More questions? 2. More questions? 3. Please join me in thanking Dr. Yulun Han. And